Hello ladies, it's Mr. O'Sullivan. Today we are going to be doing our last lesson of unit number 3, linear functions. Our lesson today is lesson 3-9, interpreting linear functions, and this is an edPuzzle assignment. So even though we have Zoom today, you're actually going to be doing this lesson on edPuzzle. You're going to join our Zoom. I will release the edPuzzle link. You will come back at the end of the Zoom, and then we'll go over any clarifying questions and even possibly do an example. So please pay very close attention to this video. That way, you can do very well in the edPuzzle assignment. Today's learning target is I can interpret a linear function by analyzing slope and y-intercept in a real-world situation. So all these problems that we're doing today are real-world situations. That's where the application math comes to life. So what we're going to be doing is we're going to be looking at functions that are linear. So remember, linear is y equals mx plus b. That's how we look at linear functions. And if you remember in the past few days, a lot of the times our variable hasn't been x. Our variable has been like w, t, h, m, etc. So the m represents our slope, or our rate of change, and the b stands for your y-intercept, or your start point. So this is how much you are initially starting with. So the first example we're going to be looking at today is the cost C in dollars of running a particular factory that produces W widgets can be modeled using the linear function C of W, remember not C parenthesis W, C of W equals 1.25W plus 2,175. Again, the cost C in dollars of running a particular factory that produces W widgets can be modeled by using the linear function C of W equals 1.25W plus 2,175. Well, if you look, this is basically the exact same thing as y equals mx plus b. I have my y equals right here, because remember, C of W is a fancy way of saying y equals. I have my slope of 1.25. I have my x, which is w, and then I have my y-intercept of 2,175. So let's go through some of these examples. Part A, how do you interpret the fact that C of 100 equals 2,300? So if you think about it, whenever we do function notation, this is our x value, and this is our y value. So when I look at this, I'm basically saying that I am plugging in 100 to get 2,300. But the thing is, I can't write down I plugged in 100 to get 2,300. I want to know what those numbers mean in relation to the problem. So if you look, the cost C is your y value, and then W is your x value. So if I think about this, I'm making 100 widgets, and it will cost $2,300. So 100 widgets will cost $2,300. And that's all you need to know for that. Part B, give a physical interpretation for the two parameters in this equation, 1.25 and 2,175. I don't mean physical, I mean, what do they mean? So if I look at the 1.25, we said before that that was our slope. So let's color code this. 1.25 is our slope, but we need to now explain it in the context of the problem. So for instance, if I have one widget, it will cost $1.25. If I have two widgets, it'll cost $2.50. So $1.25 is the cost to make one widget, or each widget. Now, the 2,175 is your y-intercept. And we know that that's our start point. So basically, this is the startup cost, like the amount of money you need to start producing your widgets. let's go on to C. The independent variable. Remember, your independent variable is always on your x-axis. And in this case, our x value, or our x-axis, would be where we produce the amount of widgets. So the independent variable in this case isn't time, it's widgets produced. Now, part D, what is the dependent variable? Well, your dependent variable lies on your y-axis, and it's your y values. So if I look, we said that C, or the cost, is our y values. So the cost to produce widgets is our dependent variable, because it depends on the amount of widgets produced. Let's go on to E. Calculate the cost to produce 12 widgets. So the first thing I'm going to do is I'm actually going to rewrite my equation. C of W equals 1.25W plus 2175. And I want to find out how much it costs to produce 12 widgets. So everywhere I see a W, I'm going to put a 12. So I have C of 12 equals 1.25 times 12 plus 2175. You can type this right into your calculator and tell me what your final answer is. When I type that into my calculator, I get C of 12 to be equal to 2,190. So it'll cost $2,190 to produce 12 widgets, or widgets. Part F. The cost to produce W widgets was $2,220. How many widgets were produced? So in this case, I don't know the amount of widgets that were produced. So I'm going to rewrite my equation, or my function. So C of W equals 1.25W plus 2175. So I know that the cost was 2,220. So what I can do is I can substitute that in for C of W. And I want to solve for W. So remember, whenever I solve an equation, I want to get my x's, or in this case, my w's on one side and my numbers on the other. Well, if I look, I already have my w's here. I have a 2175 I want to get rid of. So I have to ask myself, how do I get rid of that 2,175? Well, I just subtract it from both sides of my equation. When I subtract 2,175 from 2,220, I get 45. So I have as my equation, 45 equals 1.25 W. Now remember, I always told you that if I don't see an addition sign, a subtraction sign, or a division sign, then it's automatically multiplication. And the only way to get rid of or cancel out multiplication in our class is to divide. So I'm going to divide both sides of my equation by 1.25. So when I divide, I do 45 divided by 1.25, and I get 36. So I can say W is equal to 36. So what that means is that it would take 36 widgets, and it would cost $2,220. Let's go on to our next real-world situation. So it's the summer, post-pandemic. The Jackie Robinson pool in Harlem is being filled at a constant rate by a pump. The volume of water in the pool, V, in gallons, is given by the equation V of T equals 65T plus 280, where T is the time in minutes that the pump has been on. So again, the Jackie Robinson pool in Harlem is being filled at a constant rate by a pump. The volume of water in the pool, V, in gallons, is given by the equation V of T equals 65T plus 280, where T is the time in minutes that the pump has been on. Remember, this is linear, so I can say y equals mx plus b. So my y value is my v of t, my slope is 65, and my y-intercept is 280. So I have to look at this first question, part A. What does the 65 represent? Well, the first thing we can do is we can write down that the 65 represents our slope. That's the first thing we can say, but we can also say that it is 65 gallons per minute. So I am putting water into my pool at a rate of 65 gallons per minute. So water is being put into the pool at a rate of 65 gallons per minute. Now, what does the 280 represent? Well, we just said before that the 280 was our y-intercept. And we know that our y-intercept is our start point, our initial value. So if we're talking about water, we're saying that there were already 280 gallons of water in the Jackie Robinson pool. So I can say that there were already 280 gallons of water in the pool. Now let's go on to C. What is the independent variable? Remember, our independent variable is our x-axis. The independent variable is where we put our x values, so this is our x-axis. And if we look at our equation, where we have our x value is where our time is. So we can say time is our independent variable. And that time is in minutes. Part D, the dependent variable. So when we look at dependent variables, this depends on your x value. So in this case, we're looking at our y-axis or our y values. So if you look in our equation, where we have our y is where v of t is. So basically, we're saying that the gallons of water in the pool is our dependent variable. Now let's look at E and F. E. How many gallons will be in the water tank after 10 minutes? So basically, how many gallons will be in the Jackie Robinson pool after 10 minutes? So I'm going to rewrite my equation. V of t equals 65t plus 280. So 10 is my t value or my time. So everywhere I see a t, I'm going to put a 10. So right here and right here. So I have v of 10 equals 65 times 10 plus 280. So all I'm going to do is type this into my calculator. I don't need to do PEMDAS because a calculator will get it right the first time. So 65 times 10 plus 280 is 930. So after 10 minutes, there are 930 gallons of water in the pool. So it's slowly but surely getting filled up on a hot summer day. Letter F. If the Jackie Robinson pool can hold 1,482.5 gallons, how long will it take to fill it? So now we basically take our equation, V of t equals 65t plus 280, and we have to ask ourselves, am I given my time or am I given my y value? Well, if we look, 1,482.5 is your y value. So everywhere I see v of t, I'm going to put my 1,482.5. Because I want to find out how long it'll take to fill up the pool to that length, or that amount. So now this becomes a two-step equation, so I have to ask myself, how do I get t by itself? Well, if I look, I have a 280 on this side. The only way to get rid of that 280 is to subtract 280 on both sides of my equation. So I do 1,482.5 minus 280, and I get 1,202.5. Now, our final step, 99.9% of the time, is just to divide. So I'm going to divide both sides by 65. And I get t is equal to 18.5 minutes. So it will take 18.5 minutes, or 18 minutes and 30 seconds, or 18.5 minutes to fill the Jackie Robinson pool to 1,482.5 gallons of water. So that's the level of difficulty you're going to be given in this class for the most part. Occasionally, we won't give you your slope or your y-intercept. You'll have to solve for it, but we can go over that another day. So if you have any questions, please email myself, Miss Townsend, or Miss Jimenez. And don't forget, tomorrow you have a quiz review, and then on Wednesday you have a quiz. Have a great day, ladies.